Hey everybody, welcome back. This is lecture, I don't know, is this 21? Yeah, something like that. It's all about geospatial analysis. We're going to be talking about maps and fun things, but first I can show you the map to the sleeping cat. So, other things I want to show you the map to is the next couple of weeks as we finish out the course. So our course reminders, what do we have coming up? Well, I'm going to talk in 1 minute about our guest lectures, but just besides the guest lectures, this Wednesday, the 2nd of December, is going to be a review for exam number 2. So please come and ask some questions. On Friday, we're going to have assignment number 3 is going to be due. So that's also should be on your radar. Things are coming fast and thick because on Monday there's going to be that exam, right? And then the Friday after that, the 11th, it's going to be assignment number 4. And then finally on the 18th of December, which I don't know why that says Wednesday. I think that's the 3rd time I've done that. It's a Friday. Friday the 18th of December is when your final projects are due. Okay? So everything's happening really, really fast. Don't worry too much about the assignments 3 and 4. They're pretty easy. They're not meant to take up a lot of your time, just to introduce you to a couple of concepts. One other thing I would like to mention is that the teaching evaluations are coming. So if this is your first quarter at UCSD, you will find out all about them. They are called the CAPES, and that stands for something really awesome that I will never quite recall. But fundamentally, it's the time when you can tell the university and all of your fellow students what you think of this class and your instructors. So to do my job better, I need these kinds of official evaluations. So it's been really nice to get your feedback continually during the quarter, but these are the things that are going to end up, as they say, going down on my permanent record. So I would really, really like you to fill out these teaching evaluations, please. Tell us all about the course and about my own work and about the TAs and how they're doing, okay? So yeah, please fill out these CAPES. I'd really appreciate it. And you will really appreciate it too, because I'm throwing out a 1% extra credit on your entire course grade if every single person in the class, no, that's too much. Not every single person. If 85% of you fill out your student evaluations, everybody gets a brand new car, as Oprah says, right? No, everybody gets 1% extra credit, okay? So please, please, please fill out your teaching evaluations, your CAPES, when they land on your inbox. I believe they are going to be landing on your inbox on Monday, the 29th of November. That's my understanding. All right. So as I said, that's all the stuff that's not the guest lectures, because the guest lectures are happening too. So first up is going to be Ben Welsh. He is the data and graphics editor at the Los Angeles Times newspaper. So they do amazing work with all kinds of, election infographics and visualizations of fire hazards for people that have been living through wildfires, doing deep dives and looking through large amounts of data, doing journalistic investigations. So he's going to tell us some pretty cool stuff and also be a good resource for people that are interested in giving back to society through data science. Secondly, we're going to go to, so that's going to be, it's going to be Monday, November 30th. Did I just do that right? Yeah, right, November 30th. So, and it's going to be a live Zoom at our class time. So our normal class lecture time, which is 3 p.m. I know many of you may not have gotten used to that because many of you haven't been coming to office hours, which are at that time. But please, please, please come. You will be getting participation credit for coming. And I'm sure you would like those extra points. You will also benefit greatly from showing up at Monday at 3 p.m. because you're going to get a chance to ask somebody who's pretty high up in data science of journalism some very interesting questions, I hope. So take a look, please come. The second one, there we go. So the second guest lecture is going to be Jacqueline Nolis and Emily Robinson, and they together are the authors of Build a Career in Data Science, which is a really excellent soft skills book. It's about all the things that the university is not going to teach you. So their live Zoom meeting with guest lecture and Q&A is going to be at December 4th, 3 p.m., the same Zoom meeting that, again, we are supposed to be having for a lecture. All right. So, geospatial analysis. It's very important that you understand that there are loads of ways to make maps, and there's loads of ways to misuse maps. One of the ways in this funny little joke here is just to take anything and plot it on a map and think, oh, I found something interesting, right? So what does tend to happen, what's the secret to this little joke, is that if you plot anything interesting, it's pretty likely to just turn out to be the population map with the hot spots where the big cities are. Okay? So what we want to show you today is how to do this kind of analysis right, and not end up thinking that subscribers to Martha Stewart Living and consumers of furry porn are the same sorts of customers. All right. So today's learning objectives are to describe those benefits and limitations of geospatial viz, and take it a step further and look at the specifics of statistics and inference when we're in the geospatial world. It's a little different than what we've been talking about so far. So to kick us all off, let's take a look at maps themselves. They are been around for a long time, but the very earliest ones could hardly be called maps in the way we understand them. They are pictures of what exists, but they don't have any kind of realism to the level that we expect of maps today. Now, obviously that has developed over time. And one of the ways in which that has developed over time is because we have started to understand that space and time are basically the same thing. Ooh, deep, right? Sounds like we're hanging out at 3 in the morning talking to each other with a beverage in our hand. But it's kind of true in a very factual sense, okay? So if we wanted to figure out where we are in the world, and we are, say, relatively ancient, living a couple of hundred years ago, we have a hard time, okay? We can figure out where our latitude is. We can figure out how far north and south we are pretty easily, because all you need is some sort of device to cite how far the sun is above the horizon at noon, because the sun is always going around the equator. So if you're very, very far north, your view of the sun is quite low in the sky. And if you're at the equator, your view of the sun is quite high up in the sky. Okay, so knowing how far north-south you are, your latitude, dead simple. But longitude, knowing how you went around, how far you've gone around the Earth's circumference, that is a different matter, much harder. So there have been devices for dealing with this for a long time, the kind of latitude problem of sighting the sun above the horizon. And you could, in principle, use the same trick to figure out longitude, but the problem is that you need to sight off of things that you would only know where you were if you knew exactly what time it was. So you could sight Saturn's moons and figure out how far you were around the Earth, but that would only be provided you knew exactly what time it was to know exactly where Saturn's moons should be. Okay, so this is why we were waiting to understand longitude, to understand exactly where we were going east-west. We had to wait several hundred years till somebody could invent a clock that could keep accurate time on a ship. If you may have some vague sense that long time ago that all clocks had giant pendulums and they swung slowly back and forth, and that giant pendulum, well, doesn't do so well on a ship rolling in the water. Okay, you can't keep accurate time with a pendulum in the water. So the mechanical clock was basically why Britain became the giant empire that it was in the 17th century, is because they invented the clock that enabled them to do longitude. All right. So after that invention, we got maps that looked a lot more like the real truth as we know it today, because they could start to measure longitude and know where the ship was as it's going around the coast, and therefore draw an accurate map. So in a very real sense, for the first maps, the maps themselves were the data. They were the data, visualization was the map, and that was all anybody was interested in. So you can see additional refinements. At this point, at 1787, they've got the clocks and the measurements down to the level of this being basically as we understand the coastline today. Modernly, we use GPS satellites, and we're doing exactly the same thing. Space is still time. So what you're doing when you have your GPS in your phone is it's getting signals from 4 or more satellites, and what those satellites are sending are clock ticks. Okay? And by knowing the clock tick of a satellite and knowing which satellite it is, you know how far away that satellite is, because you're hearing the clock tick, which is however long, however many micro femto something seconds it is behind what the current time is, tells you how far away that satellite is. And when you can know the distance to 4 satellites, you can know your location on the Earth. Okay, so space is time, and that's how we make maps, right? But how we make maps, there's no one clear way to make a map, okay? There are different projections, ways to map out our Earth, because our Earth, of course, is a 3-dimensional object. It is a sphere. But all the maps that we're used to using modernly, or, on paper back in the day, they are not globes. So we need a way to project a 3-dimensional object, like these guys playing sumo wrestler, into a 2-dimensional world. Okay? And when we create maps like this, what we're doing is we are making an abstraction, a paper projection, laying this 3-dimensional globe onto this 2-dimensional map for our convenience. And every such projection has problems. Okay? So I'm going to try to play you a short video. I don't have a direct hookup from the audio of the video into my recording rig, so we're going to use my microphone and see how that goes. My apologies for poor sound quality and for the noise it's going to make while I move the mic right now. All right, this is a famous little clip from The West Wing, which, maybe is not really your cup of tea, but it's all about maps.
Hi, I'm sorry.
Oh,
Sorry to be late.
not a problem.
I'm CJ Craig.
Of course you are. I'm Dr. Jon Snow, with Dr. Cynthia Sales, and Professor Donald Huke.
Hugh.
Huke.
Okay, and you are the Organization of Cartographers for Social Equality.
Well, we're from the OCSE. We have many members.
How many?
4,300 dues-paid members.
What are the dues?
$20 a year for the newsletter.
Let's start.
Wait, I want to see this.
This is Josh Lyman.
Indeed you are.
Josh, this is Dr. Fallow and
Hi.
News Merry Men.
Yes.
Should we begin?
Yes. Plain and simple, we'd like President Bartlett to aggressively support legislation that would make it mandatory for every public school in America to teach geography using the Peters projection map instead of the traditional Mercator.
Give me $200 and it's done. Really?
No. Why are we changing maps?
Because, CJ, the Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World.
Really?
The German cartographer, Mercator, originally designed this map in 1569 as a navigational tool for European sailors.
The map enlarges areas at the poles to create straight lines of constant bearing or geographic direction.
So it makes it easier to cross an ocean.
But
Yes.
it distorts the relative size of nations and continents.
Are you saying the map is wrong?
Oh dear, yes. Look at Greenland.
Okay.
Now look at Africa.
Okay.
The two land masses appear to be roughly the same size.
Yes.
Would it blow your mind if I told you that Africa is in reality 14 times larger?
Yes?
Here we have Europe drawn considerably larger than South America. When it's 6.9 million square miles, South America is almost double the size of Europe's 3.8 million.
Alaska appears 3 times as large as Mexico, when Mexico is larger by 0.1 million square miles.
Germany appears in the middle of the map when it's in the northernmost quarter of the Earth.
Wait. Relative size is one thing, but you're telling me that Germany isn't where we think it is?
Nothing's where you think it is.
Where is it?
I'm glad you asked. The Peters projection.
It has fidelity of axis.
Fidelity of position.
East-west lines are parallel and intersect north-south axes at right angles.
What the hell is that?
It's where you've been living this whole time. Should we continue?
Uh-huh.
So, you're probably wondering what all of this has to do with social equality.
No, I'm wondering where France really is.
Guys, we want to thank you for...
Okay, so all that fun aside, I hope that was a reasonable video experience on your side. I'm going to find out when I finish this recording. Projections, the way in which you choose to view a map, does have strong implications, and there are different projections for different tasks. Okay, so I am going to show you a few such projections just for fun. So here we have a nice little toolkit published in D3. So D3, I think you've seen a few times now, is one of the cool web visualization toolkits. And a lot of the coolest web visualizations, especially dynamic moving ones, are done with D3. So this is just rolling through a gazillion different projections of the map to give you a sense of how many there are that I'm sure you didn't know, and that each one has its own different things which it has fidelity to. Okay? So, not that I want you to memorize all these different projections, but just to be aware that, hey, this is something I might want to learn more about, especially if I'm ever working with global level data. All right. So, why do we study geospatial analysis? Well, it's been said since, the ancient days of 2008 that maps are the killer app, right? You may not be old enough, actually, to remember a time before everybody had a smartphone, when people actually carried around paper maps or didn't have a map at all most of the time. And it's often been said that the reason why the smartphone really took off was because finally everybody realized that the whole map and GPS thing really was a very important and big leap forward. Okay? Before that, nobody had quite seen why they should spend so much money on these things. So why are maps the killer app? Well, I mean, we all want to know where stuff is. We want to obviously be able to get around, and we like to be able to get around without going through here be dragons, okay? Without getting our ships eaten by the Kraken or whatever else is going to happen. So along those lines of visualizing danger, probably the first really big application of this kind of spatial analysis that we can point to in history is when Jon Snow, who's a famous physician from the 19th century, figured out a way to stop a cholera outbreak using maps. Okay, so you're saying Jon Snow, and in your mind, I'm pretty sure you're thinking this dude. But in fact, we're talking this dude, who was the personal physician to Queen Victoria, along with a bunch of other crazy lifestyle choices he made. And at the time, he was one of the very few people who had an idea that in fact diseases like cholera were not caused by foul odors, but rather particles and something you ingested. So he was an early proponent of the germ theory of disease, right? That there's something physically that transfers to start a disease. Before that, they thought it was miasma and vapors and, nasty smells that made people sick. So when there was a cholera outbreak in a local area near Broad Street, what Jon Snow did is he realized that if he really thought that the disease was being transmitted through some sort of contact, that he would have to map the territory and figure out what was going on in order to think about how it spread. Because if you thought it was just vapors, then the map wouldn't really show anything, right? It's just the night fog of London coming through and making people ill. But if it's something that people are touching or ingesting, then the map will help you. So in this visualization, what you're seeing here are little tick marks. So everywhere that somebody died, there's a tick mark at that building. Okay? So buildings over here, some of these apartments had, 4 people die or 5 or 3. Okay? And over here, this building had quite a few more. Thought Jon. So when we zoom out, it gets even weirder, because here we are once again. Here's Broad Street, that same location we were just looking at. But nearby businesses like the brewery here and this workhouse had many fewer deaths than you would have expected given their proximity to this location. Well, it turned out that the brewery workers, they didn't drink water during the day. They might have been drinking something else. And so that was what led Jon Snow to realize that, in fact, it was probably the water pump right here on Broad Street, this pump right there, that was the source of the cholera outbreak. So Jon Snow marched down there and removed the pump handle on his own orders, and lo and behold, the cholera outbreak in this local area stopped spreading. And it was shown that, in fact, it is foul water that could cause it. So, data science saving lives. Kind of reminds you of another pandemic, maybe? I don't know. So, we still continue to use geographical visualizations to help us understand diseases. Here we have a map of, two maps, I should say. One map shows you the mean solar radiation, and you can see that the further south you go, obviously, the more sunlight you have throughout the year, and the higher overall levels of UVB that you get. Well, it turns out that that map of higher radiation from the sun is anti-correlated with a number of diseases. So it kind of looks like there are several diseases, for instance, including breast cancer, where the rates are higher up north where there is less sunlight. And if you just saw one of these things, you might think, random chance, maybe this is a false positive, right? Well, there are several such diseases that look quite a lot like that. So here's multiple sclerosis, which, just like the breast cancer map, has much higher prevalence of the disease up north compared to down south. So in fact, there are a number of diseases that are like this. This one is also multiple sclerosis again. But what I wanted to get across with this graph is that this is not a map per se, right? This is showing us latitude, degrees latitude. So this is north, and this is towards the equator, and then further south. Okay? So the further north you go, the further away from the equator you go, the lower the level of solar radiation just in terms of amount of sunlight that reaches the ground, right? And you can see from these curves that these different regions mostly go up. There are a few exceptions. And some of those, can be explained away by various other things. But what I wanted to get at with this kind of a graphic is that this is not a map, but it shows geographic information. And there are times and places when you want to show data on a map, and there are times and places where it's better to show it just as a regular plot, but where one of the axes is related to space. Okay, so I'm going to continue to do the shorter lectures, so I'm going to take a little break right now, and I will talk to you all again in just a few minutes. Bye for now.